So let's review this real quick. Okay, so you might recall last, I don't remember what day it was. It was prior to, maybe like Wednesday, Tuesday, something like that. We talked about converting forms of quadratic functions, right? We said we had 3 forms of quadratic functions. Maybe let's write those down real quick. So the one we've used, well, what's standard form? So standard form would be something like f of x or y equals plus c. Okay, so what are the 3 parameters there then? The three numbers that we can control to change the function? A, B, and C. A, B, and C. Good. What about vertex form? A times
X minus h squared
okay,
plus k.
plus k. So we're pretty familiar with that one, right? We've done a lot of graphing already of functions in vertex form. The 3 parameters, obviously a, h, and k, we're very familiar with those 3, right? And then the last one,
Factor.
f of x equals
A minus x plus
x minus p times x minus q. Okay, and there the parameters are a, p, and q. Now, what are the meaning of p and q there? The zeros, or the x-intercepts. If they're real zeros, they're the x-intercepts, right? Where the function crosses the x-axis. Okay. So we want to do 2 things today. I want to review the stuff I forgot to put the assignment up on. So we want to review how do we convert between forms. Now, really, practically speaking, all we really typically do, we very seldom would we ever try to convert directly from vertex form to factored form. Typically, we're either going, between standard form and vertex form, or standard form and factored form. Right? And if we really wanted to get from vertex form to factored form, well, we could always just convert to standard form first and then turn that into factored form, right? So what do those things look like? Well, if we were going to try to go from factored form or vertex form to standard form, that's just simplifying. That's just PEMDAS, right? All we would do is, if we were going to convert, if we were going to do this, we're going to start there and end there, what would we do? We would just FOIL this stuff out, right? We looked at a couple examples last week, and the notes are up. We would just FOIL that stuff out and then distribute A, right? Collect like terms, and then it would, simplifying turns it into that form. Sometimes we call standard form simplified form, because when you follow order of operations and simplify, that's inevitably where you end up, okay? If we wanted to do, instead, what if we wanted to go from here? Same thing. We're just going to follow order of operations. We're going to
draw it out.
We're going to multiply that out first, right? We're going to expand that out, FOIL it out, or whatever. We would use our pattern to what we would do, right? What was our pattern again? A plus b squared equals what?
A squared plus 2ab.
2ab plus b squared. Good. Okay, and b could be negative. If it's something like x minus 5 squared, then a would be x and b would be negative 5. We just would follow that same pattern, right? Okay, so we would just, we'd expand that out using our pattern, distribute the a, and then add like terms, and once again, we would just end up, after we simplified it all, we just end up in standard form. Question?
Are you recording?
I am recording. Thank you for checking. Okay.
I do is recording,
So what's maybe a little bit tougher here is to do the other stuff though, right? To start in standard form and reverse the arrows and go into one of these forms. We've already practiced one of these a lot, right? We've already practiced this one We already spent a lot of time on that. That's just factoring, isn't it? Right? We
Yeah.
practiced our factoring patterns and PEMDAS and all that stuff earlier in the year, and you'll get more practice with it. But that one, we've already done quite a bit. This is the one that we spent a little bit of time on. How did we go from there down to, whoops, other way around. How did we go from here down to there? We complete the square. Right. That was the process of going from standard form to vertex form. So let's just practice one of those. So what if we wanted to convert this quadratic function into vertex form? So we've got something like, I'm going to write it in the form y equals, how about? So we've got y equals 2x squared minus 24x plus 23. Well, what do we do?
Minus 20.
Okay, good. So we're gonna complete the square, which means on the side where we're working, right, the side where we're trying to complete the square, we've got to get this into the form x squared plus some number times x. We used to call it b. That's fine. We can call it b. But if you call it b, sometimes that's confusing because is it the same b as that b? No, it's not. It's not going to end up being the same b. So we get x squared plus some number times x by itself, right? That's where we have to start. So our steps are obviously going to be subtract 23 from both sides and then what?
That one thing, that's.
Well, I mean, what do I have to do though first though? I don't have it in my starting form. Divide by 2, because I can't have the 2 in front of the x squared. So I'd have to subtract 23 from both sides. There's step 1. And that's going to give us y minus 23 equals
X squared.
2x squared minus 24x, right? Because the 23's cancel. And then you told me I'm going to divide each side by 2, right? Because I want to get those 2's to cancel. And so if I do that, I'm going to get just y minus 23 over 2 on that side. I know that looks ugly, but remember, we're just kind of storing stuff on that side for a while. And then we'll eventually re-isolate the y. But that's okay, it can look ugly for now. Over here, though, if I split this into 2 terms, what do I get?
X squared over 2.
Well,
Minus 12.
That's all that.
okay. Right? Okay, so now we're ready to complete the square. So what was our trick here? What did we have to add to both sides? Half of b, which would be negative 6, squared. So we added 36, right? And that was good because then on the right side, what did we get?
Alright. Well, usually it's the other side.
Well, it's, yeah, you're right. Typically it's the other side, it doesn't matter.
X minus 6 over 2.
There you go. So x minus 6 squared, right? Where's the over 2 stuff? I can get that. Yeah. Equals all that stuff on the other side, right? But we completed the square. So now all we've got to do is just reverse the steps that we took previously to get that y by itself, and whatever we end up with is what we end up with, right? So what's that look like? So we got our y minus 23 over 2 plus 36. What's the first step? Subtract 36. Good. So we get y minus 23 over 2 equals x minus 6 quantity squared minus 36. What's next? Multiply by 2. Okay, so if you multiply each side by 2, those cancel, right? And there we get that. So we get y minus 23 equals, if I distribute, what do I get? Okay, last step. Add 23 and we're there, right? And so finally we end up with y equals 2 times x minus 6 squared minus, what is it, 49? Okay, and that's in vertex form, isn't it? What are the values there of A, H, and K? 2, 6, no, negative 49. Okay, so we can make a sketch of that pretty easily then, right? If we wanted to. Okay, so we got that. That's if you can do that one, you got that third assignment, I guess it is, taken care of. What I want to look at today is how can we graph quadratic functions directly from the other forms. Because if you got, let's get earbuds and stuff away. I don't want to see any earbuds in here when I'm teaching. So put those away, please. We know how to graph quadratic functions in vertex form. We've had tons of practice with that. I'm not at all worried about that. But do we have to go through the process every time of completing the square in order to graph a function that starts off in standard form? We always could, of course, but that's a lot of work, right? Is there a shortcut? Let's see if we can come up with a general method. Now, we always want to think in terms of if I start completely generally and I'm able to do the problem without being specific at all, then I come up with essentially a formula. So I can always do it the same way, right? So what if we started with the most general form of a quadratic equation in standard form? We're not going to plug in any values for A, B, and C, but we want to see if we can graph this thing. Well, the easiest form to graph from is vertex form, right? So if we could make some connection, and we've actually done this before. When we developed the quadratic formula, we did almost the same steps. Right? We're going to go back and sort of rehash those again. It's good to see them again. We'd like to turn this standard form equation into the easiest one to graph, which is vertex form. Right? We already know the process. That's just completing the square, isn't it? Right? So if we were to kind of, well, we can go through this somewhat quickly here. Oops, that's wrong page. There it is. So let's go ahead and set this thing equal to, instead of calling it f of x, I'm just going to call it y. So it's a little easier to write. And Tanner was getting all messed up by completing the square on the right side. I anticipated he would, so I put it on the left side this time for him. So if we complete the square, would everybody agree? First thing I'm going to do is I'm going to subtract the c, right?
Yeah.
Then I'm going to divide by a, both sides, correct?
Yeah.
So I get that. If I divide both sides by a, ax squared divided by a is x squared, bx divided by a is b over a times x, and then I get the whole right side divided by a. Agreed?
Then you add half of b.
Good. So half of the coefficient of x, whatever's being multiplied by x, that number, which is b over a. Well, what's half of b divided by a?
b over 2.
Yeah, half means half of something is what I get when I multiply it by 1/2, right? So 1/2 times b over a is b over 2a, right? So b over 2a squared is the special number I'm going to add to both sides to turn this into a perfect square trinomial, right? So on the right side, once again, it looks horrible, but who cares? Doesn't matter. It's just a bunch of stuff that we're going to undo. On the left side, what perfect square does that turn into? X plus b over 2a, right? Quantity squared. Because that's the number that's half of what we used to call b. Half of the coefficient of x is b over 2a. So that's what's being squared when it's added to x, right? On the other side, if I square this out, if I distribute the 2 to all the factors, I just get this term. And so I completed the square. Okay. Now all I've got to do is just reverse those steps. So I could subtract this term from both sides, right? So it ends up on the left side of the equal sign. I could multiply both sides by a to get rid of that. Do we agree? Okay. If I distribute the a to both parts, I'm just going to get a times the quantity x plus b over 2a squared. And then here, if I multiply b squared over 4a squared by a, doesn't that just cancel one of the a's? A on top cancels with one of the a's on the bottom. So I get that. Equals y minus c. And the last step is just add c to both sides, right?
Yep.
So that's what I end up with. Well, let's put the y on the other side, and that's vertex form, isn't it? Right?
Yeah.
See what it is? I've got, and it really is, I've got y equals a times x minus h, right? So that must be x minus negative b over 2a, right? H is negative b over 2a. Everybody agree? Okay. Now I know, put this in kind of context again. I know that looks terrible, but we've done something really cool here because we haven't specified what a, b, and c are. So this is going to work for any values of a, b, and c, right? This is always going to be true. And this is how we got the quadratic formula. And then I get plus whatever else is left over, all this junk, that's just going to end up being, those are just constants. And so whatever number that calculates becomes k, right? So those are the values of my, of my parameters. I get h equals negative b over 2a. There's my a, right? My vertical dilation factor. And there's k. So what was our goal here, though? Our goal,
Easier way to do it.
okay, our goal was to be able to directly graph a quadratic function in standard form. This is pretty useful information then, right there, isn't it? This tells us the x-coordinate of the vertex, right? The x-coordinate of the vertex is always given to us by the formula h equals negative b over 2a, right? So let's take a specific example then and just apply this. What if we had, something like that? What if we wanted to find the graph of this quadratic function? Let me make this a little bigger. Okay, now before I go any further though, let me just pause here for a second. Now don't lose your train of thought, because that's the thing about math. You can't get distracted. You have to really kind of keep your thought focused on this. Are there any questions though so far? Yeah, we can really all, say it again?
Can we just use that
Yeah, exactly. That's what we're going to do, right? We did the heavy lifting here to come up with the formula. Now we don't have to do it every time, right? We know that every time we do this,
h equals negative b.
we're going to come up with that, right? We're always going to get the same result. We always know that h equals negative b over 2a if we start with a quadratic equation, a quadratic function in standard form. Okay, so let's apply it to our example then. So what was that formula again? H equals what?
Negative b over 2a.
Okay. So what are the values of a, b, and c? Because this is in standard form, isn't it? Ax squared plus bx plus c. So what's a? Say it again. 3/4. What's b? 9. And we don't really care about c, do we? All we need are those two things. So if we plug in our formula, this is going to give us h equals negative 9 divided by 2 times 3/4. Right? So I could do little, on the bottom, I could just make that 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So h equals negative 9 over 1 times 2/3, which is what? Negative 6. Okay? So that's pretty important. So we already know that if h equals negative 6, that's half the battle, right? How would I find k? Keeping in mind k is just the y-coordinate. If I know the x-coordinate of any function, how do I find the y-coordinate? What do I do? Plug it in. Evaluate the function, right? Remember, that's what f of x does, right? We've said clear back in algebra 1, you guys said a million times, f of x is just a fancy name for y. Well, literally, y is equal to f of x, right? Not only is it a fancy name for it, it's exactly equal to it. So if I plug this value into my function, I'm going to get back the corresponding y value. So what is my function evaluated at negative 6? Well, we just got to plug it in and see. So f of negative 6 equals 3/4 times, what's negative 6 squared? 36. Plus 9 times negative 6 plus 28. So what is that? We're going to get 27 minus 50. So 27 plus 28 is 56. Minus 54 is 2. So h is negative 6, k is 2, right? What's the value of a?
It's 55.
Is it 55?
Yeah.
Oh, whoops. You're right, 55, so it's 1, isn't it? Whoops. What's the value of a? 3/4, right? The value of a doesn't change. A is the same in all three forms of a quadratic function. A means the same thing. It's always the vertical dilation factor. So this is pretty easy now, right? All we got to do is we know that we're going to pick the parabola with a vertex where? -6, +1, right? And it's going to have a vertical dilation factor of 3/4. So we'll pick a convenient point. What would be if I think about a regular parabola, right? Regular parabola, I go regular parabola. I go over 1, up 1. I go over 2, up 4. I go over 3, up 9. What's a convenient y value to multiply by 3/4?
60.
That one, right? Instead of going over 2 and up 4, we're going to go up a times 4. Well, a was 3/4 times 4 equals 3. So we'll only go up 3, right? That makes sense? So this has been squashed a little bit, right? We're going to multiply all of the y values of the parent graph by 3/4, which is going to make them 3/4 as big as they used to be, so a little bit smaller. So then we can go to our graph and we're going to, let's graph this thing, and then we'll just slide down and find the one that fits. Right, so let's do that stuff. So we said -6, +1. So there's -6, +1. And we said instead of going over 2 and up 4, we're going to go over 2, yep, and up 3. And then we'll do the same thing on this side. And so,
Oh. I bet you can. Okay.
yeah, that's pretty proud of it. Okay, so we just have to go find that one.
Oh.
Look at that.
No. Maybe.
No, that's just so satisfying. Okay, so that's our answer, right? Okay?
You should give us all 50 boys to do at home.
Wouldn't that be nice? Okay.
I don't know where I put it. You also need a projector. That's just one problem with that. I don't know where I put it, not the money.
I'm gonna take a picture of that just for the notes. How about it? Probably be a good idea. That's so good. I gotta take a picture of it.
Video it slide you down foldable projector. Okay, one of these days you gotta let them solve it up there, grab one, like
Okay. Next Friday football fun. How about?
That should be this Friday. One group that has like
Okay.
Too big, dude. I just
Okay, last one. Let's look at one more of these. So how about? Well, actually, no. We got two more. Try one like this. Okay, what if you're supposed to write that one in standard form, as a quadratic function in standard form? Now just don't say anything. Everyone think about what your strategy is going to be here. How are we going to take that graph and write it in standard form? And there wasn't, I mean, the connection, there's no really obvious way to graph something from standard form. We have to use our new formula, right? What's the easiest way to link, it's easiest to link a graph to which form? vertex form, right? Okay.
And then you convert it.
Ah, okay. So that's our strategy, isn't it? Right? All we'd have to do is from this graph, and this is stuff we did last unit. What are the values, just by inspecting the graph, what are the values of A, H, and K? Well, H and K are easy. What are H and K?
Positive 2, positive 6.
So over 2 up 7, looks like. Okay, what about A? So we got to compare what we're doing to what we would normally do. So we're going, on this graph, we're going to the right by 3, and we're going down by 3. What would we normally do?
9.
Go up by 9. Okay, so we normally go up 9. So then what's the value of A? Negative 1/3, good. So A would equal negative 3 over positive 9, which is negative 1/3. And now it's easy, right? All we'd have to do is start this thing off in vertex form, right? Because we know A and H and K, and then just simplify it. Follow PEMDAS and put it into that form, right? Okay. What about one like, let me get a picture.
You've got a lot of ways you can write that.
What do you mean?
But you do a lot of this. You do horizontal. But you over the y-axis maybe. You go over the x-axis.
Maybe?
You could.
Okay, last one. This one's pretty easy to do. Okay, what form is that in? Factored form. Okay. So if we wanted to graph this one, it's in factored form. Let's think how we could do this. So all we really need to find the graph of a function is we need to find some points that lie on the function. That's all we ever do. Like in these last examples, when we superimpose those graphs, and I did such a great job. Still pretty proud of that one. All we really did was we found 2 points, right? And that's all we needed to guide our parabola. It was just a couple points, right? So how about this guy? We just need to find some points. What are some easy points to graph from this function? What do you think? Okay, the x-intercepts. Yeah, why not, right? We could set the function, this is equal to y. So why not set this thing equal to 0, right? If we set this equal to 0, we're asking the question, when does y equal 0, right? Well, that's easy. It's already factored. By the zero product property, what are the x-intercepts? Negative 3 and positive 5, right? So we already know, and we called those P and Q. We already know that P is negative 3 and Q is positive 5, right? So we know right away that the x-intercepts need to be there, and there. So those are right, okay? How could we locate the vertex?
Okay. You look for
Now think about that. What's the vertex? So to find the vertex, we just need its coordinates. It's x and y coordinates. The x coordinate is really easy to find.
slope.
No? But let's just stop thinking specifically for a second. Let's just think about properties of parabolas. Parabolas are symmetric, right? They have folding symmetry about their axis. We call it the axis of symmetry, which is just a vertical line through the vertex, right? That's literally called the axis of symmetry. So if these things have to have this folding symmetry, this reflective symmetry, and we know that the x-intercepts are here and here, what does that tell you about where the vertex has to be? It has to be halfway in between. It has to be the average of the x-intercepts, doesn't it? Right? Because if I were to fold this paper, what has to happen is I have to be able to draw one of these in wet ink and fold the paper over its axis and get the other point, right? They all go together in pairs because they have that symmetry. So all I need to do is find the halfway point. You've been doing that since grade school. That's just averaging. So negative 3 plus 5 over 2, the average of the x-intercepts is what? 1. 2 over 2 is 1, right? So we know that the vertex has to be on the line, the vertical line, x equals 1, right? How do we find out where? If I know the x coordinate of a point, how do I always find the y coordinate? Plug it in. There's my function, right? So if I plug in x equals 1, what do I get? Well, f of 1 just equals negative 1/4 times, what am I going to get? 2 times, no, 4 times negative 4? So what's that work out to be? Negative times a negative is positive. I'm going to get 4, 1/4 times 4 is 1, times 4 is 4. So what do you know? This actually is that's the right parabola, isn't it? It fits. Okay, everybody see that? Okay, what are the odds? About 1 out of 6 or something like that. Okay, you can work on these things. Get some questions answered. That's it. That's all I got.